Hello everybody. This is going to be our second topic in our third unit. The third unit is on basically circular and oscillatory motion. And hopefully yesterday we did a group lesson together where we talked about period and frequency. And today we're going to expand on that in a asynchronous lesson that you can watch individually. As I often do, I just want to explain why I chose this lesson to be asynchronous. I've got a couple of reasons. One, whenever we finish up a unit, sometimes it's kind of nice to have some flexibility. And so this is a lesson that you can watch at home, you can watch in class on your headphones, you could watch it before or after the designated time, but it's nice to have flexibility to be able to do this whenever you want to. And maybe right now you need to redo some tasks or like you haven't handed in everything yet. And so that's the nice thing about this is that you can do the lesson, and rather than having to be forced to pay attention to a group lesson, you have the flexibility to do this on your own pacing and time. The other reason why we're going to do this one asynchronously is that this one involves a lot of the math calculations, and I always like to try to do those ones asynchronously so that way you can speed things up or slow them down if the math is you're finding it either too easy or challenging. Usually that's the thing that requires the most variation between students. So, anyways, with that being said, why don't we start? This is our second topic. We're talking about harmonic motion, and sometimes it's actually called simple harmonic motion. You can see here with the acronym here, SHM, simple harmonic motion. It basically can't talk. Let's do this again. Simple harmonic motion describes any scenario where there's repetition. That's the key word, where something repeats its motion over and over again. And we should have discussed frequency in our last topic. I'm just going to go quick find a slide here to point out how this works again. Here would be a good example of things that are in a repetitive motion, right? Where there's something that is repeating. This crazy little pattern is repeating over and over and over again. A heart rate monitor would be a great example of a repeating pattern where we want it to happen consistently on the same frequency, basically, right? And so it repeats its motion over and over and over again. And one of the words we're going to use here is that it has to have what's known as a restoring force. Because I mean, although those previous examples of a heart rate monitor, those would be a good examples of patterns. Those don't really count as motion necessarily. We actually need an object to be moving. And so if you have an object that is moving back and forth over and over and over again, then we need to have what's known as a restoring force. Because if you're getting something to move out, Newton's first law would suggest that objects in motion stay in motion. And so if something's moving out towards our right, well, we need it eventually to turn around and go back towards our left. And so we need something to cause it to do that. And then once it starts going to the left, Newton's first law would say it would keep doing that for forever until an unbalanced force gets to turn around and go back the other way, right? And so if you have a scenario where things are going back and forth, we need to have what's known as the restoring force, which is the thing that causes the object to move back towards its equilibrium point. And so this concept, hopefully it just makes some intuitive sense. The equilibrium point basically would be the middle, right? In this diagram that I drew right here, the middle of this diagram is the equilibrium point. And it's constantly being pulled back towards that equilibrium point. At this point right here, where the object is moving like that, it's really being decelerated. You would have a negative acceleration right now because it's slowing it down. Otherwise, this object would keep moving for forever. And then eventually, that acceleration then makes the acceleration be kind of in a positive direction, where now you have a positive acceleration as it's going this way, right? And so now it's going to speed back up again. But as that object then keeps going too far, well, now we need to slow it back down into negative acceleration, because otherwise it'll just keep speeding up for forever, right? And so it always alternates between a positive and a negative and a positive and negative acceleration, as it always tries to find balance. And the best examples I can think of for this are either springs or pendulums. And I think I'll use a pendulum to describe it at first, because really it's going to go back and forth and back and forth and back and forth, and it's always being pulled towards that middle equilibrium section there. So let's show you some more theory about this, and then we'll move on to some of the math examples. Actually, no, we're going right to a force, actually. We're going to a formula. This is known as Hooke's law. And if you know about Robert Hooke was a contemporary of Sir Isaac Newton, and they were actually rivals, quite bitter rivals, in fact. This is a tidbit that doesn't matter all that much right now, but Sir Isaac Newton apparently, the theory is that Isaac Newton was responsible for Hooke's painting being mysteriously missing, because every physicist always had a painting drawn of them, and we don't have one of Hooke, and we wonder whether that's due to Einstein or due to Newton. Newton had a lot of rivalries with other people. Anyways, that's not really important. Hooke is the one who kind of figured out how the formula worked, okay? Because he realized that every elastic object had to have this restoring force, or a force that like brings things back to where they came from. And this would be a good example of something that we've already done in this class. We should have done a lab on friction where we made a slingshot. And when we made our little slingshot, we pulled backwards. And this bow and arrow kind of makes sense, is that we're going to have a force. Ooh, we should use a color you can see. I think yellow will show up really nicely. We're going to use a force that we're going to want to pull backwards, right? And if we pull backwards a negative distance, and that negative distance is known as x, then what's going to happen is a restoring force is going to want to make the arrow fling back the opposite way. And we use Fs for that. And some kids think that the S stands for springs, and that's fine, but like I don't know why we used S, but we used the word restoring force. Because the idea is that it wants to restore, it wants to return. Let's use that word, return. These objects want to return to their point of equilibrium. And so the point of equilibrium on the bow would have been right here. And so therefore, as it gets pulled back, this makes it want to go to there, right? What usually ends up happening is things overshoot, and this thing will, like, the wire will wobble back and forth for a little while, because it'll overshoot this way, and then it'll overshoot this way, and overshoot this way, and it'll go back and forth, right? So, anyways, Hooke came up with this formula. It allowed him to calculate a restoring force, which that was this word right here. This is the word return force. And it's based on really two things. There's a linear relationship, and you can see I have the picture up here. There's a linear relationship between the distance that you expand something. So if you pull further back on a bow and arrow, there's going to be more force. If you only pull back a little ways, there's not as much force. So the distance that you pull something and the restoring force have a direct relationship. Pull harder on the bow and arrow, and it will have more force to it. The other thing that matters, though, is this value here called K, and we've been starting to learn about constants in this course, hopefully. This is a constant for your elastic, and really every elasticy material has a different like stiffness to it, if that makes sense. The analogy I'll use is a bed mattress. There are some bed mattresses that are very soft. Think Goldilocks and the Three Bears. This bed is too soft. This bed is too hard, right? Like the bears. You get what I'm saying here, right? So everything has a different soft or hard value to it when it has compression or expansion ability. And so basically, if you have a very, very stiff bow, it's going to take more work to pull back on it, right? But if it's a very flimsy, loose kind of piece of wood and bow that's on there, it might be easier. So long story short, this is a new formula that we get to add to our list. And it's appropriate because we just finished our section on forces, and we now have one more force formula to add to our list. So let's try an example. These are very basic. These are not overly challenging in terms of what we're going to start off with. What we have is a spring, and the spring has a constant of 18.5 Newton per meters. We want to figure out the restoring force when the spring is expanded, right? And so what we're doing is we're taking the spring and we're pulling it outwards. So if you can kind of imagine that this is a spring right here, right? What we're doing is we're pulling it outwards. And so it's like a slinky that's been pulled out, right? And so we're expanding at 15 centimeters. So it's 15 centimeters longer than it normally is supposed to be. So here's your formula to find the restoring force. It's equal to negative kx. And a lot of kids get so thrown off by this negative because they're like, should I make things negative or positive? Look, guys, ignore the negative. The only reason why the negative even exists in this formula goes back to this picture right here. If you pull back on the string, the restoring force wants to then send it back the opposite way. That's the only reason why there's a negative in this formula. But it's usually best to just ignore the negative, honestly. Like, just skip the negative. I know it says it in the formula, but that's only because things are going opposite directions. Just make the formula kx. So we know our k value is 18.5. And we know that it's being expanded an extra 15 centimeters. So that means it's going to be 0.15 meters. So this will tell us how much force this slingshot, this spring has. 18.5 times by 0.15 gives me, with two significant digits, 2.8 newtons worth of force. And the direction of that force is going to be like back towards equilibrium. It always goes towards equilibrium. this is to the point where I'm not even going to write this sentence anymore. Because like what's going to happen is if you stretch this thing outwards, the force is going to want to try to pull the spring back towards the equilibrium, right? If this is where it normally was supposed to be and you stretched it outwards, it's going to want to come back, right? I'm thinking of like car shocks and struts when I think of this example here, right? Where sometimes it's going to bounce up a little bit and down, and we're either going to expand or compress the spring, because that's really the next one right here. Now what we're going to do is we're going to compress this spring. So now the spring has been shoved in a whole lot. It's been squished down. There's like a ton of extra weight in the back of your truck, and all of a sudden your shocks are riding a little low because of the fact there's so much weight in there. And so what used to be basically 15 is now riding a little bit low, and it's low by apparently 20 centimeters. You solve this the exact same way. All right, let me just erase the one number that changes. The only number that changes is now it's going to be 20 centimeters. So this will be 0.20. So 18.5 times by 0.20 in this example would give me 3.7 newtons of force. But the direction is still really the same. It's still back towards equilibrium. Now this purple one that you compressed, it's actually going to need to go back up, whereas this one's going to need to stretch back down. So I mean, I guess up and down are a little bit different, but either way, a restoring force, this Fs right here, by definition, it always is trying to go back towards the middle, right? And sometimes it kind of goes and overshoots it, and so it goes, too far this way, and then too far this way, and too far this way, and eventually it finds a way to settle itself out, and gets back to where the middle is supposed to be. So hopefully that made sense. I'm going to move on. Try another example here. Let's say that you have a spring attached to the ceiling, and I'll try to draw a bit of a picture here. So there's a spring attached to a ceiling, and so here's a spring attached to the ceiling. And normally the spring would be, say, this long right here. But what I'm going to do is I'm going to take that same spring and I'm going to stretch it out a little bit further, and the reason why is that we have a mass on the end of it. So something heavy on the end of the string is causing the spring to expand, right? And we know how far it expanded. From where it normally was supposed to be, the spring has now expanded an extra 15.7 centimeters. And that's a really key word there. This is an extra 15.7 centimeters. I could care less how long the spring originally was. The spring could have been 10 meters long or 3 centimeters long. I really don't care. All that really matters is that it's now 15.7 centimeters more than it was supposed to be. Right? And so now we want to try to calculate the spring constant. Well, just like we've done in the previous unit on dynamics, we got to build ourselves a formula. Unless the spring is oscillating up and down, our free body diagram for this is pretty straightforward. Gravity is pulling this spring and this box downwards, but the restoring force of the spring would want to bring it back up. It's unable to because gravity is preventing it from it, but if you were to take this weight off, it would fling back upwards, right? So we can now build ourselves a formula, and using the principle of uniform motion, which is basically no motion, you could then say that the restoring force has to equal gravity. And continuing to build your formula, your restoring force is equal to kx, and gravity is equal to mg. And again, kids would say, Chris, but there's a negative in the formula. And I say, I know, I don't care, right? Because the only reason we have a negative is because the negative tries to oppose the distance it was pulled. So I know there's a negative in the formula. Ignore it. Use your own critical thinking skills. Don't get so tied in to having to use positives and negatives everywhere. Build those critical reasoning skills. So anyways, the whole point of the question was then to solve for the spring constant. So here, this will solve for the spring constant. K will be equal to mass times gravity, which is what's pulling you down, divided by how far the spring expanded. So plugging some numbers in, let's look back up and find them all. Mass was 1.5 kilograms. We're on Earth, so gravity is 9.81. And it was compressed by, it said 15.7 centimeters. So let's make that 0.157 because it needs to be in meters. Okay. Standard unit is in meters. Standard mass is in kilograms, standard units in meters. So if you ever get kilometers or centimeters, you always need to convert. So anyways, I'm typing stuff in here. I've got a spring constant with 2 significant digits. Looks like we've got 94, and the units are going to be newtons per meter. That is the unit for a spring constant. K is measured in how many newtons it takes to move something a meter. So the basic idea is that if it takes 1 newton to move something a meter, or if it takes 10 newtons to move something a meter, well, the 10 newtons per meter, that must be like a stiffer spring, because it's going to take more effort to basically to bend it. So there is a relationship between how much force you have, and if you were to take force and if you were to divide it by your x value, the slope of this graph, by the way, would be your spring constant. F divided by x would be equal to k. So the more you can move it, the more force you need. Okay, like I always say, if that made sense, awesome, move on. If you need to ask for some help, if you're able to in class right now, pause the video, ask me for help, or make a note of this, and when you're free and able to the next time, ask me. Otherwise, let's move on and talk about some more examples here. Now what we want to do is we want to figure out the acceleration of a mass on the end of a spring, and this is now a horizontal spring. Now, I'm just changing up the way we're going to draw it. We're going to assume that friction is negligible, so imagine that what we've got here is a table. And somehow right here I've got like a, I don't know, like something firm that can't be moved, like some sort of big, large block. And what I'm doing with this big, large block on the table, if you can kind of picture how this works, that's the table here, I guess. That'll be the edge of the table. It's not a bad drawing, Chris. Okay. Imagine that a spring is protruding from the outside of this block here. And the outside of this block, it normally would go this far. That's as far as the spring would normally go. But what we've done, if I can just add an extra blue color to it, is that it's actually going to go a little bit further than normal. We're pulling it out. And so if I were to draw a free body diagram on this, somebody is on this spring, they're pulling this way an extra bit. And by pulling it an extra bit this way, it's causing the spring to expand, right? This right here is stationary. Our box is stationary. And we're pulling the spring out. So where I finished drawing in black is how far the spring would normally go. And I am stretching it 12 centimeters further. Don't worry about whether it's positive 12 centimeters or negative 12 centimeters. Just use your own common sense with positives and negatives and figure out how we should fit that, right? So ignore the negative kx, ignore the negative part of the formula, and just solve it with good reasoning skills. So anyways, here's the point here. There was a mass on the end of this, so why don't I draw the mass in black here, just because I just want to point out that the blue is the extended section. So we've got a small little mass on the end of this. It is frictionless, we're saying here, which is not how real life would work, but let's assume that what's going to happen is there is a force that's pulling this outward, but wouldn't there be a restoring force wanting to cause this box to fling back the other way? And so if I had like my hand, if this was my hand, there's my hand around it. If my hand is holding this object right here, I should add more fingers. If my hand is holding this object right here, that's really the green arrow, right? My hand is pulling the object out, but the restoring force wants to fling it back the opposite direction. And it's going to, so I'm going to ask you for the acceleration, right? So what we need to do is we need to then consider that acceleration. Well, as soon as I let go of this box right here, so as soon as the hand is missing, so I guess I'll just erase the hand now, there we go. Now there's no longer an applied force kind of keeping it in place. There's really only one force happening, right? So no longer is there this green force holding the box in place. The only force that we have now is this restoring force that wants to pull it back towards its equilibrium point, right? And so if I were to then consider a free body diagram, I mean, really there's just the one force. So I could then say, well, normally F is equal to ma, but there is only one force. The restoring force would be equal to m times a. So therefore, if I want to solve for the acceleration, I'm now building myself a formula. Acceleration, I'm just going to flip the order here if that's cool, is your restoring force over your mass. But your restoring force is equal to kx over m. Again, ignore the negative. It's not really that purposeful. And okay, we're ready to plug in numbers. So k is my spring constant, which was 54.9 newtons per meter. So, I mean, not quite as strong of a spring as our last example. We're going to stretch it 12 centimeters, so that's going to be 0.12 meters. We have to divide by the mass of the object that's being accelerated, which is 0.250. And since friction is not in play, remember how, like, if there was friction in play, I would have to then subtract a force of friction, because friction would be trying to prevent my motion. But if we assume friction is negligible, just in this particular example, then here's our answer, 54.9 times the 12 centimeters divided by 0.250, that was in kilograms. I have an acceleration of 26 meters per second squared. So now I know how fast this object is being flung backwards, and I mean it might even get flung so far that it actually crashes into the barrier I've drawn over here. Or it might only go part of the way back, and then it might oscillate back and forth, right? Like eventually the spring is going to compress. You gotta remember that as this swings this way, the spring is going to get very compressed in here, and the box might only make it that far because it's going to get compressed. I think of subway cars, or if you've ever ridden the C train in Calgary, when the C train gets to the end of the line, they often put a spring at the very, very end of it so that it doesn't go crashing into like the very, very edge of your rail lines, right? So this is your rail. Imagine this is a rail line right here. Now, then what they might have is that then when the train, it's getting messy now, but the train is on here, they put a spring right here so that it compresses the spring and it slowly brings it to a stop. Okay, let's move on. When working with forces, we can use free body diagrams. However, we can also calculate what's known as the period of the spring. And the period of the spring basically would reference the idea that like maybe it's going to swing back and forth, right? Maybe it's better to like diagram this using a vertical spring. Imagine this is my roof right here. And what I have is I have a spring that's going like this, right? And what's going to happen is I might pull it down, and so eventually it'll be stretched down to here. And then the restoring force will bring it back up. And so then this spring goes back up to here. But Newton's first law keeps it in motion, so it eventually goes up to, say, up here, and then the spring gets compressed. Well, then the restoring force wants to pull it back down, and I mean, so would gravity, honestly. And so then eventually it comes back down to here, and now it's at equilibrium, but Newton's first law kind of keeps it in motion, and so then it eventually goes down to here again. And if you get where I'm going with this, this is going to repeat a pattern that's going to go back and forth, and this fits a sinusoidal pattern. And for any of you who have either taken Math 30-1 or are taking 30-1, that's kind of the pattern to it, is this thing's just going to oscillate. That's the word we use, oscillate. Hence the word oscillatory motion. So it's just going to go up and down and up and down. And so we've actually found a formula for the period of a spring. So remember, period is how long it's going to take. This is basically little t time. We often use little t as time and big T as period, but they kind of mean the same thing. In the same way that A is acceleration and G is the acceleration due to gravity, in a similar sort of way, big T stands for period. It's how long something's going to take. So if I want to know how long it's going to take for this thing to go down and back and up and back and get back to here again, the period is the amount of time it would have taken to go from here to here. Right? That would be known as your period, the amount of time that took. So it might have taken 3 seconds to go all the way down and back and up and back and get to here, and that would be a period. Say 3 seconds. So the formula has been discovered for it. It's fairly straightforward. You just need to know 2 values, really. You need to know the mass of the object that is oscillating, and you need to know the spring constant, and that's it. So this is more or less just to kind of plug her in the formula, and yeah, let's give it a try. So let's figure out the period of the spring in the previous example. We did an example a while back. It was horizontal, if you remember, where I had that picture of the table. It's all messy now, so I won't even go back there, but I had that spring that was coming out here, and what was happening is it stretched a little bit further. Right? And if you can kind of picture what's going to happen here, I'm just going to literally make a box, I guess. Right? What's going to happen is it's either going to stretch out. I wonder if I can glue those together. There you go. Watch this. So this is where it normally would be. And then the spring spreads out, and then it pulls it back. And then it compresses it to here. And then it goes back and forth, right? And if you can kind of imagine, this is what's really happening, right? This is at its full extension. Here's back at normal. Here it's compressed, then it's back out. Full extension, equilibrium, full compression, middle, full extension, right? So the question is, how long is it going to take to basically oscillate back and forth? And so the formula is pretty straightforward. It was T equals 2 pi, the square root of m over k, I believe. Let me just double check. Yeah, m over k. So just plug in the numbers. The mass of the object was 0.250. The k value was 54.9. I mean, this is, there's no problem solving on this particular example. Hopefully you'll understand that there will be on other examples, obviously, but on this particular one, it's more or less just plug things in, and so based on sigdigs, I believe it's going to take 0.42 seconds of time for, again, if I can illustrate it, for the spring to, let's start it all the way compressed. Make it compressed, so then it gets shot outwards until full extension, and then it's going to come back again. It'll take 0.42 seconds to do that, and then another 0.42 seconds to get to there, and another 0.42 seconds to get to there. It'll take 0.21 seconds, half of that, 0.21, to go from full compression to full extension. It'll take half of that time. So, okay, so we've learned a couple new formulas. This is really a new formula day. We've learned the new formula for restoring force. We've also learned the formula for period. In general, what ends up happening is this formula here for the restoring force, where was it? Yeah, Hooke's law right here, restoring force. It normally involves needing to work with dynamics equations. And so you're often using this force right here with other forces. Like if you look at our examples here, we made this force equal to the force of gravity, or we could make this force equal to mass times acceleration. We could add it to a list. We could have Fs minus F applied plus Fg in the y direction. You know, like you could add all sorts of forces together. It's just another force you add to your list. In general, though, this new formula here for periods, it's more or less a standalone formula. It doesn't often get used with other items. It usually just gets used the one time. So. Okay, now let's talk about pendulums. The way a pendulum works actually is very similar. It has that same oscillating motion where things go back and forth. And unfortunately, I seem to have covered up some of the words on this slide here. So maybe I'll move that down so you can see. Really should have put that there. The way it works here is that a pendulum also has a restoring force. As a pendulum goes side to side to side, the restoring force always wants to pull it back to the middle, pull it back to the middle, pull it back, right? Pull it back until eventually it goes like, you know, and it barely kind of vibrates a little bit back and forth here. Right? Now, what you need to know about the restoring force for a pendulum is you can't use Hooke's law. Okay? Hooke's law of F equals kx does not apply to pendulums. It does not apply. You need different formulas, because it's really a component of gravity. And if I can use this photo to try to explain it, just like we did inside those triangles that we drew for, you know how we drew an inclined plane? Hopefully you're fairly good at drawing the inclined plane by now, where you put an object on an inclined plane and we have the force of gravity going down, but there is the force of gravity in the y direction and the force of gravity in the x direction. This F of g in the x direction, that is the restoring force. Look at this. If I were to make that same formula right here, the way this works is that gravity is pulling this object down. But if I were to break gravity up into a couple of different dimensions, what we really have is the force of gravity in the y dimension, the force of gravity in the x direction, just like we did in the inclined plane. It's just we give them different names. We often say that the force of gravity in the y direction is Ft because it's exactly equal to the tension in your rope. Right? I mean, there must be tension in this rope, and so the Fg in the y direction must be your tension. And similarly, Fgx is actually known as your restoring force because it's what's pulling you back this way. It's what's trying to pull you towards the middle, and so it's what's pulling back. So now a couple of notes here. The larger the angle, the larger the distance the bob is moved. If you don't know the term, by the way, a bob is the fancy name for the thing on the end of a pendulum. Any pendulum that goes back and forth, bob is what we call this thing. Yeah, bob. So anyways, we got a couple of assumptions. Number one here is that when you're pulling back on this thing right here, we assume that you're only pulling back less than 20 degrees. The math will actually change if you start pulling a pendulum back like all the way up to here. I'm sorry, this is kind of messy, but if you had a pendulum that was pulled all the way back up to here, the math kind of changes once you make the angle that you pull this object. If it gets to be too large of an angle, it kind of screws up. So we assume that the angle inside here is usually 20 degrees or less, give or take. We also assume that there's no friction. We always get to try to assume there's no air resistance, no friction going on. And but that becomes the problem. The higher up this goes, the more that other things come into play. Because really it's getting pulled down, and then it's getting pulled over, and so now there's more chance of air resistance. Furthermore, we also got to consider that the mass of the string is negligible. So whatever this string is right here, we got to assume that it's pretty consistent. It's not going to stretch. And yeah, so that's a pendulum. I've got an example here that kind of talks about what actually happens truthfully in a pendulum. For those of you who've done Math 30-1, you'll recognize the start of this graph right here. In Math 30-1, this is actually the graph of y equals sine of theta. And the way that graph works is that it goes up and then back down and then up again. It's got that up and down sort of pattern to it, right? Sinusoidal, which is what we're describing oscillatory motion. Now, for the first little while, what's actually happening is as you make your angle get bigger and bigger, so as you're pulling your pendulum further and further back, it actually is approaching a sine graph. It actually has the beginning of a sine graph to it. And so if I could just go back to this complete mess that I've drawn here and point this out. Right now, we basically have an angle right here of I'm assuming this angle is like, say, 20 degrees. But if I were to pull it out to here, the angle would now be, say, 45 degrees. The most you could probably pull this thing out would be completely out to here, which would make it 90 degrees of an angle. The problem is that the way this actually works as a function is it works just like a sinusoidal function does, where it goes up and down. And the problem is it's not actually linear. It behaves almost linear for about the first 20 degrees, though. But then a linear graph would keep going straight, and the sine graph then eventually has to start turning around. And so there is not a complete direct relationship between force and displacement in this one right here. It's more or less direct, but it's not quite. So anyways, let's move on. Here's kind of a picture that illustrates the idea of that restoring force, right? So you take your pendulum and you pull it out to here. So let's just say we give it like 15 degrees so it doesn't have to worry about being too far out, right? Well, the restoring force is going to want to pull it this way. And then what's going to happen is inertia, once it gets to here, it's going to keep going. And then the restoring force is actually pulling back on it. And as the restoring force pulls back on this, it slows it down until eventually it comes to rest. And then the restoring force keeps pulling this way, and then it brings it back towards the middle until it's past the middle and it starts to go this way. Now its motion is this way, but its restoring force wants to pull it back towards the middle. And because its motion is this way, but because, so this is its velocity is this way. But because the restoring force is pulling in the opposite direction, it slows down, right? And then eventually it comes to a stop, and then eventually it does go back the other way. And you can just, it keeps going back and forth, right? So anyways, let's try an example here. We're going to try to calculate the restoring force for a 2 kilogram mass attached to the end of a pendulum. And so we're going to do a lab on this. One of these days on my calendar, I should have shown you that we're doing a lab. Let's just assume you have a pendulum, and this is the pendulum bob, and it's supposed to be going straight down. And what we're going to do is we're going to pull the pendulum out to here. And so I'm going to draw a dotted line out to here and illustrate this is where we're going to pull it to. So imagine this is some person's hand right here. No, that's the worst hand I've ever drawn in my life. Yeah, anyways. There's a hand. Someone is pulling back on this pendulum, and we know it's getting pulled back 10 degrees. The question is, how much restoring force does it have? Hopefully you'll recognize that the restoring force, if I use another color, the restoring force is actually trying to pull it this way. Right? It's trying to pull it towards this location right here. And so red is my restoring force. Here's how you draw this triangle. The way you draw this triangle works something like this. You always draw this going straight down. And in green, the straight down force is the force of gravity. And in a similar way to how we drew the triangles on the inclined plane, I have to draw one going like this, which is the force of gravity in the y direction. And I have to draw one that goes like this, which is the force of gravity in the x direction. And if I were drawing a free body diagram, I should point out that there is still one more force in play. I'll use this blue line right here. There is the force of tension. And so what I know is that the tension force needs to equal the FGY component. Those two have to be the same. So force of tension equals the force GY. Otherwise, there would be no slack in the rope right here, right? If the rope is tight and there's no slack in the rope, then these two forces are equal to each other. But there is no force to balance out FGX. And so therefore, FG in the x direction is your restoring force, which is this little red arrow here, right? This red arrow that I drew right here, it is that side of the triangle, and it's what's causing, let's pick up the red one, it's causing this object to then go in the x direction and try to basically whoop, go along, there we go, along that trajectory there. See that? So red is causing that. So long story short, you just gotta remember, how do you find an FGX? Well, FGX is mass times gravity times sine of theta. And hopefully you're getting better at that. So mass, 2 kilograms, gravity 9.81, sine of 10 degrees, we are done. I don't mean to be so flippant about it. Ooh, not FF, FS, restoring force. So I don't mean to be flippant about it, but this is not meant to be an overly taxing example yet. We just need to plug numbers into our formula. So 2 times 9.81 times the sine of 10 degrees gives me a restoring force of 3.4 newtons. And if I were to kind of describe which way that restoring force is going, it's initially going this way. However, it's eventually going to kind of go this way, and then this way, and then this way, and then this way, until eventually the object is right there. And then, as soon as the object starts going on this side over here, that restoring force will actually start wanting to try to pull it back this way. And that's why the object slows down, right? Because as this box goes back and forth, if I were to describe it, right here it's got a restoring force that's going that way. And then the object goes here, and so the restoring force kind of turns a little more sideways. And eventually it gets to right here, and there is no restoring force, because there's no reason for there to be a force anymore, because gravity would just pull it straight down. But inertia will then take it out to here, and what ends up happening is the restoring force will then pull it back this way and therefore slow it down. And eventually this object will go out to here, and it'll get slowed down some more. It'll get out to here, it'll get slowed down some more. Now it'll finally stop. And then after it stops, it's then going to, because of this red arrow, get pulled back towards the middle. Move that out of the way. Pulled back towards the middle. And then once it's literally right at the middle, there is no reason for a restoring force anymore, because literally the only force you have now is the force of gravity pulling down. There is no component to it. So inertia keeps it going, and you rinse, lather, and repeat. So, okay, hopefully that made sense. I'm going to move on, because we got a couple examples, then we're going to call her a day. This is a visual picture of it, kind of illustrating all the forces in play. You got tension going this way. This is mg cos theta. This line right here that's kind of missing, the one that would go on this side of the triangle right here, is the restoring force, but it's really what's causing this thing to move that way. So. Okay, we're getting close to the end. What do I got left? I got a few examples. Okay, just reminding myself. So let's try an example here. Let's say there's a kid on a swing, and I know its equilibrium point is 0.35 meters. That's how far back we've been pulled above the ground. So I don't know if I can draw this all that well. Here's kind of like a crossbar, if you can kind of picture that, of a swing set. And this is the swings right here. There's kind of a curvy section there, and now there's a child sitting in the swing set, right? And if you can kind of picture this side to side, the kid's going to go this way, and then he's going to go that way, right? That's the swing set going back and forth. And so in terms of what we've been asked to solve for, first we want to do is we want to figure out if the swing gets pulled back 0.87 meters from the equilibrium point, and we know the length of the swing is 2.67 meters. Let's figure out how high above the ground this thing is. So, although I've drawn the picture like this, it may work better just to treat it like a pendulum. And so if I were to draw a second diagram, here's the ground, and this would be the pendulum above the ground. And so normally the kid is going to be from here to here, 0.35 meters above the ground. But as the swing swings back and forth, right, if I could take my purple and kind of illustrate the same way, it's going to swing, let's curve that a bit more. It's going to swing back and forth like this. At some point, your child, which is a pendulum that's on the swing, is going to be over here. And it says that it was pulled back 0.87 meters. Okay. And the other thing you're being told is the length of the swing itself is 2.67 meters. Well, you might wonder, why is that important? Well, in order to solve this formula, you guys might recall that one of the things we're going to need is theta. We're going to need this angle right here. And I can solve for that angle. Oh, I don't like this drawing though. Let me draw it nicer for you. Okay. So here's your pendulum right here. We're going to pull the pendulum back to right there. And some of the things that I'm going to tell you is that we're pulling it back 0.87 meters. But the length of the pendulum, the length of the swing itself, was 2.67 meters. The reason why we need that is that we need to solve for this angle right here. We need that angle to kind of go forward in the question. But like there's a little triangle buried in there, right? Can you see that triangle? The way we're going to solve it is by saying that sine of theta is going to be equal to the opposite over the hypotenuse. Then we'll say sine of theta. Well, in this little triangle right here, the opposite of this angle right here is 0.87. And the hypotenuse, I mean, this is going to be a nice little 90-degree angle right there. The hypotenuse is 2.67. So if you want to solve for theta, you just need to inverse sine both sides. And if you inverse sine both sides, you'll get your angle by itself. So if I were to sine inverse 0.87 divided by 2.67, I now know my angle is basically 19.0166, something like that, degrees. And I know I'm going to use that answer later again, so I'm going to store that as answer A. But that's what I wanted to point out in this example here, is that based on the information I gave you, trigonometry is such a huge part of physics. You need to make sure you understand how your trigonometry works. And so I've now solved for this angle right here. It appears as though this kid on the swing got pulled back 20 degrees, basically. So, okay, well, for the first question, it actually wants to know the height of the swing above the ground, which means that there's actually one more thing I could solve for. What I'm really being asked to solve for is this height value right here. I want to find that value there. And in terms of problem solving this, there's really no physics. This is still all math at this point. Because the way we're going to discover this value is that we know from here to here is already 0.35, right? We already know that from where the kid was above the ground was already 0.35. What we're really lacking is this distance right here. I'll call it x right now. It's basically from here to there. We need to know how high he is above his equilibrium point. And to solve that, what's going to work really well is why don't I solve for from here to here? I'm going to solve for that value right there. And the reason why I'm going to solve for that value right there is if I then take 2.67 and I subtract this value right here, 2.67 minus this value right here will give you this little component. And the reason why it's 2.67 is that if from here to here is 2.67, it's the same thing from there to there. So what's essentially going to happen is I'm going to take 0.35 and I'm going to add this little extra height right here. But to find this extra little height right here, which I'm going to call x, I really need to find this value here. I'll call it y, I guess, right? And so if I can find this y value and subtract it from 2.67, I'll get x. And then once I have that, then if I add up to 0.35, I know how high I am above the ground. So let's give that a try now. So the first thing I need to do is I need to do Pythagoras' theorem. What I really have is a triangle that looked like this, where this side is 2.67, and this side over here is 0.87. And so I need to solve for this, which I think I was calling y. So Pythagoras' theorem would yield me this. 2.67 squared minus 0.87 squared, all square rooted, that'll be equal to y. So I may as well find that value. 2.67 squared minus 0.87 squared. Square root the whole shebang. And y is 2.52 meters, which I'm going to store as letter B. So if I could erase some of the mess that I've got going on inside here, I've now determined that I know that this value right here is B. But I know that from here to here is going to be 2.67 minus B. Hopefully that logic makes sense to you. If it doesn't, can you make sure you ask at some point as to how I figured that out? But what I know then in my diagram here is that if this right here has now been, I guess I called it y, now I'm calling it b. Apparently I'm just changing letters everywhere. But I know that I need to know the next little distance. That's going to be 2.67 minus b. And then maybe I can pick this up and move this a little bit lower so it's not all in the way. Yeah, there we go. And so that's where the pendulum would normally sit. And so if I were to draw that out right here, the pendulum would normally sit here. So that's the extra height. But then I need to add the extra 0.35 meters above the ground. That will give me the height that this thing is above the ground. So I'm going to take 2.67 and minus b. But I'm going to add on an extra 0.35, and now I've got a height above the ground of 0.495, which with, what do I get for sig digs? 2 sig digs is 0.50 meters above the ground. So, interesting question, hey? Because it really didn't involve physics formulas. So often students will ask me, Chris, I don't know which physics formula to use. Can you just show me which physics formula to use? Now I'll be able to solve it if you just give me a formula. But like, I didn't use a physics formula at all. I used entirely trigonometry. So please let me know if I lost you there. So there, we solved for the height of the swing above the ground. And the angle from the equilibrium point, I already solved for that back here when I did sine. And I still have this number stored as A, by the way, because I knew I was going to need it later. Because the last question is, what's the restoring force? And we've done one of these before. The formula for the restoring force then. If I can redraw this out, so this is like the pivot point. And there it is right there. The free body diagram would go like this. There's a force of tension pulling something one way, and there's a force of gravity pulling it this way. I'm going to put gravity on. Oh, I can't put gravity on that side. I got to erase it. Hang on. I'm going to put the force of gravity over here because I want to break this up into the force of gravity in the y direction, force of gravity in the x direction. I know that the tensional amount must be equivalent to the force of gravity in the y direction. But I also know that the force of gravity in the x direction is the restoring force. Force of gravity in the x direction is equal to mg sine theta. So that's all I need. Mass. 26 kilogram kit. Gravity was 9.81. And then that angle for theta, I stored it as A a long time ago because I knew that I was going to need to know this angle here at some point. So, even though when I solved for it as though there was like a line across this, right? Like when I solved this the first time, we kind of put a line just flat across, but the angle still hasn't changed. Whatever angle is in there, it's still the same angle. It's actually the same angle in here. It's similar triangles. So 26 times 9.81 times the sine of letter A gives me a restoring force with 2 sig digs of 83 newtons. And at this point, that force is trying to pull me this way. But is it always going to pull me this way? No. Because eventually it's going to change and it's going to want to pull me this way. All right, as it swings back. Okay, we're getting long on the video here. Let's move on here. I got 2 slides left. There's a formula that tells you the period of a pendulum. So it's very, very similar. Very, very, very similar to this formula way back here that tells you the period of a spring. You have to make sure you're careful. I believe on your formula sheet, they're like right next to each other. This formula right here tells you how long it takes a spring to oscillate back and forth. Well, this formula right here tells you how long it takes a pendulum to oscillate back and forth. And all you need to know is how long your pendulum is and what the force of gravity is. And that's it. A cool little note, by the way, it doesn't even matter how heavy your pendulum is. We're going to test this in a lab one day, but if I were to ask you to plot how the period of a pendulum relates to its mass, it doesn't at all. Mass does not affect how a pendulum works. And one of the reasons why we know that is due to, like, remember the story of Galileo dropping cannonballs off the side of the Leaning Tower of Pisa? Mass is irrelevant for some things, right? I mean, if you have a higher mass, it does not make things go faster. There's more force if you have more mass, but a higher mass does not actually make them travel faster. And since time, t, period, is a measure of how fast it's going to travel, it's not going to travel faster if you have more of it. So let's try some examples and we'll call it a day. Determine the length of the period of a pendulum with a length of 16.7 meters. As long as you know how long your pendulum is, and as long as you know what planet you're on, which is probably Earth, all you got to do is this formula here. 2 pi times the square root of 16.7 divided by 9.81. This will tell you how long it takes to go back and forth. So 2 pi times by the square root of 16.7 divided by 9.81. And I got I'm going to need 3 sig digs, 8.20 seconds. So that means it's going to take 8.20 seconds for this pendulum to start here, swing all the way there, and swing back. It's there and back. Don't forget that. It'll be 4.10 seconds for it just to go there. So it'll be 4.10 seconds to go there, and 4.10 seconds for it to come all the way back again. So all that matters is how long your pendulum is. If you have a small little pendulum, like if your pendulum was only this far, then it would happen faster to go back and forth. But if you have a longer pendulum, it's going to take longer because it's got to travel more distance. So hopefully that made sense, because I got one last example, then we're wrapping things up. One of the cool things that pendulums are actually used for is they can be used to calculate acceleration due to gravity. We've found different ways of calculating acceleration due to gravity. One of them is through using the formula g m over r squared. That is one way that you could calculate the acceleration due to gravity. Another way is through kinematics. You could just drop objects. You could find a velocity initial of 0. You could measure a time value. You could measure a distance value, and then you could solve for acceleration. That's another way that you could calculate acceleration due to gravity on planets or on just at locations. But another option is this new formula here. The formula was period was equal to 2 pi times the square root of L over G. So we could actually, if we know the remaining variables, we could actually solve for gravity. Here's how it would look. You'd have to take T and you'd have to divide by 2 pi. That would then give you the square root of L over G. Then you would have to square both sides because you're going to want to get rid of the square root sign. So you're actually going to have T squared over 4 pi squared. That'll be equal to L over G. You have to make sure that when you square the T squared, you also square 2 and pi. So that's 2 squared becomes 4 and pi becomes pi squared. And then our last step is we have to now rearrange this for G. And so without showing too many of the algebra steps, this will be how the formula will look. You'll times G up to this side over here. You'll times the 4 pi squared up to this side there. And you'll divide the T squared down here. But I've now made ourselves a formula for gravity. All you need to know are two variables. The length of a pendulum, which was 2.75. And you need to know the period, which is 3.33 seconds. Don't forget to square that. Which means if you have 4 pi squared times 2.75 divided by 3.33 squared, we have now calculated gravity at this location to be 9.79 meters per second squared, which that would make sense because gravity on Earth is about 9.81. So either we didn't measure these values quite perfectly because maybe the period wasn't 3.33, maybe it was 3.34 or 3.35. So we always need a margin of error. But we're actually going to do this in one of our labs. We're going to confirm that the amount of gravity is actually supposed to be 9.81. And one of the ways you can do this is by setting up a graph where on one axis you put 4 times pi squared times L. On the other axis you put T squared. And you curve straighten your data and find a linear line, the slope of that line being G. And so that should be one of the things that we're going to test out in the lab one day. So, okay, my run time's at 53 minutes. That's about where I want to end. I always try to keep these things to about an hour or less. So as always, if you have questions, make sure you let me know. Maybe you watched this video in class. Maybe you watched it on your own time. It really doesn't matter. That's what I love about the flexibility behind this. Hopefully you're making good use of time and resources. If you have questions, please ask. That's what I like about doing this asynchronously, is that a lot of times kids aren't going to want to ask when I do a group lesson. But if you've got like a piece of paper nearby, write down some questions as you think about them and ask me as you get a chance to. So, okay, thank you everybody. We will talk soon. Have a great day.